The big surprise about self-replicating machines is that the hardest part is not fabrication. It is trust. A system only replicates in the industrial sense when it can keep making useful descendants, generation after generation, without silently losing precision, calibration, or control. As of 2026, the best demonstrated examples are still partial and highly constrained. They show the direction, but not full industrial closure. The most legible public case is RepRap, a 3D printer lineage that can fabricate some of its own polymer and structural parts. Yet it still depends on externally supplied motors, electronics, sensors, firmware, precision rails, power systems, and feedstock. That boundary line matters. Partial recursion is real. Complete autonomy is not. So what exactly separates a clever demo from an operational system you would deploy in a mine, a polar site, or a lunar outpost? The core issue is closure across generations. Each generation has to reproduce more than parts. It has to reproduce tolerances. It has to reproduce calibration routines. It has to reproduce inspection capability, repair procedures, and the rules for rejecting bad output. Without those, replication becomes a drift machine. It keeps producing descendants, but the descendants stop being reliable tools. That is where molecular systems become an unexpectedly practical guide. In biology, self-replication is dominated by information templates, error thresholds, and environmental dependence. Leslie Orgel framed this clearly back in 1987, treating the origin of self-replicating molecules as a constraint problem. If error rates are too high, information cannot persist. If the chemical environment is wrong, replication fails. Industrial recursion has the same logic. Your template might be CAD files, firmware, or process recipes. Your chemistry might be impurities, thermal cycles, or toolware. The deeper lesson is that replication fidelity, not copying speed, sets the ceiling. A second finding is that metrology is not a side quest. It is the controlling layer. A recursive factory that cannot measure its own outputs cannot guarantee anything about its descendants. Even if it can print housings and machine brackets, it may still need externally supplied measurement standards, reference artifacts, or calibration equipment. That is why metrology recursion is such a sharp research question. Can the system reproduce, or at least maintain, the instruments needed to certify the next generation? Or does measurement remain a permanent external dependency? A third finding is economic, and it reframes the whole conversation. Mark Staley's 2022 analysis treats self-replicating machines as a capital formation and scaling problem, not just a robotics problem. When a system can produce more production capacity, it changes growth dynamics. Output is no longer limited by how fast you can buy and ship new equipment, but that same feature creates incentive and governance problems. If replication is cheap, who authorizes it? Who audits it? Who is liable when descendants diverge? That leads to the strategic crux, containment, and certification. Any system capable of manufacturing production equipment or critical replacement parts needs explicit governance controls before it scales. Think authorization logs, rate limits, provenance records, and certification checkpoints. Without those, the failure modes are not subtle. You can get junk replication, where outputs look plausible but degrade. You can get hidden dependencies, where a supposedly self-sufficient system quietly relies on a few fragile suppliers. You can also get uncontrolled proliferation, where capacity expands faster than your ability to test, verify, and safely integrate it. Now consider where recursion is likely to show up first. The near-term pathway is not a factory that builds a full copy of itself. It is repair-first recursion. Printing fixtures, housings, jigs, spares, and repair tooling is a practical way to increase resilience. It reduces downtime, and it reduces the number of parts you must stock or fly in. Over time, those capabilities can climb the closure ladder from simple structures to more demanding subsystems. Remote and off-world settings make the logic even sharper because logistics dominate. Alex Ellery's 2018 Lunar architecture frames self-replication as a bootstrapping concept, a way to multiply capability when resupply is costly. Still, published lunar machine designs remain design studies, not deployed factories. The gap is not imagination. The gap is closure, especially in feedstock transformation, precision components, power, repair, and verification. So, if you are allocating capital or setting policy, the most actionable move is also the least glamorous. Require a closure map for any recursion-capable system. What is produced internally and what is externally sourced? What generation depth has been certified? What metrology dependencies remain? What governance controls exist and who holds the keys? Without that map, self-replication is marketing. With it, recursion becomes an auditable engineering program. The memorable line is simple.